So we'll use that same turbine, the SkyStream, as a case study. And if you remember those wind roses that I showed you maybe 10 minutes ago, basically it was just under 5 miles an hour, or 5 meters a second winds in that area where I clicked. That was just around Kingston. So if you look at that, then on an average, basically you can expect that you're down in this low end of your turbine. That's kind of startling. You think you're going to be out here. Well, what does that work out to? Remember I said that there's seasonal variabilities, and you have to look over the year. So on a monthly basis, if we're out at about 5 meters a second, then what happens here? I think this was shifted one way. I believe it was over here where the line intersects. At about 5.5 meters a second, you can anticipate about 400 kilowatt hours a month out of that. Sure, there's going to be times when you're going to generate a lot more. There'll be times when you look up and the turbine won't be spinning. But that's on average what you can expect. So you need to take this power component, and this is what everybody talks about with wind turbines, and turn that into how much energy you're going to make. So, one color didn't show up. Oh yeah, I guess it did. It's right there. So this is what I was talking about with the seasonality of the two renewable energy electricity generators. Typically our loads are quite constant throughout the year. Now this is totally dependent on how you heat your home. Obviously if you have baseboards, this is going to be very high in the winter months. But most homes that use natural gas a lot and things like that, their loads are generally consistent. So you have to make sure, that's the first step in all this, is to really understand your loads throughout the year. So you need to understand what your line is. What we can do from that is I can tell you how the sun is going to act, and then we can also approximate how the wind will act. So what you can do from that is you can say, hey, like I can make this much wind and cover my loads. I can put in solar, and then the wind will come back up later in the year, and pretty much you've got your loads met, right? It's these areas in here that are going to be tricky. So if we look at what the manufacturer estimates at 300 kilowatt hours a month, in the Wind Atlas, they do their calculation a little bit differently, pretty much the same. It's about 325 kilowatt hours a month. Maybe. And we take that 30 kilowatt hours a day, multiply that out, you get 930 kilowatt hours a month. So you get about a third of your loads met from that turbine. So I'd say that's the starting point you need to be at. You need to really understand your loads, and then you start picking your renewable energy to meet those loads. So now to use the power, there's a couple different ways. Am I still good for time? Yeah, it's still 8:30, is that right? So the first is what's called net metering. So basically this is, if you're drawing in power from the grid, you can basically supply your loads in your home with wind and take less from the grid. That's the first option. The second option is this standard offer contract. The same thing that you can use for solar where you sell it for 42 cents, but wind gets 11 cents. Much less attractive. We're hoping that that's going to change too, but there's no guarantees. And so what I'm going to talk about is what we can do now and what really does make sense. Yeah. Why?
What's the government's rationale for not making it the same?
Well, the rationale is that the Wolf Island wind turbines, 11 cents is economically reasonable. Okay, so they can make wind power in that kind of range. Small wind, no. And large solar farms can't do it at that cheap either. So that's why the rates are tiered. The standard offer program is designed to generate the bigger market. And that's where the wind tariff is coming from. So Unfortunately, it doesn't help out the homeowners a whole lot. That's why I'm going to tell you that what I would recommend is the net metering option, and I'll get into that in a second. The third option is to store it in batteries for later use. Now you can do the battery option with the other ones as well. Also, like the solar talk, if you don't need batteries, I would say not to do them. If you're connected to the grid and you have maybe one power outage a year where it's a few hours, or maybe you're at work and you don't even notice, I would say just stay clear of it. There's no reason. It's a few extra $1,000s onto your project, and you don't need it. If you're in some place where you anticipate big failures, like Muskokas or something, then yeah, that makes sense.
Back to number 2, if you had 50% solar and 50% wind, how would they know?
Yeah, they thought of that. Yeah, I guess people have tried a lot of things, but you basically have to have a separate meter for each thing, right? So you're going to get a meter that will tally up your wind, tally up your solar, and then how much you suck in off the grid. Yeah, they thought of that.
So the wind power, is it DC or AC?
Pardon me?
The
wind power?
Is it DC?
Well, it can be either. When it's made in the turbine, it's made in an AC, a wild AC and uncontrolled alternating current. Then it's usually rectified into, or it's usually changed over into DC. And then you can store that in batteries and use it if you want. Or then it can be changed back to AC in a regulated fashion so that you can use it for your appliances. So just quickly how net metering works. On the far right here, that's my sketch of what a power line looks like. And it pumps electricity into your meter, and that comes down into your panel in your home, into your circuit, your breaker panel. And that powers your appliances. Right now, you're paying about 5 or 6 cents for a kilowatt hour, and then you have the transmission costs and the debt retirement. And a blended rate, a good ballpark, is about 11 cents a kilowatt hour by the time it gets to your plug. So how it works with wind, it's basically you have the power coming in from the turbine, and this can be in DC. And this can go down into your battery bank if you have that and charge up your batteries. And the next thing from that is you can pull this DC current from your batteries into the inverter. These little boxes are things that you'll need to talk to your installer about. And basically it changes that DC into AC. And so you get this DC power in here, it's going into your batteries, it's controlling your batteries. That's what the charge controller does. It allows it to fill. If it gets depleted, your inverter pulls it off, turns that into really clean AC that you can't tell the difference between this and the Darlington nuclear power, and it goes into your panel. So in that case, what's happening is the power can go here and supply your loads. That means you have to pull less down off the grid. So essentially your bill goes down. You don't know really how much because there's no meter on it, but you get less of a bill. In cases where you're producing more than what you consume, then this power goes back out through onto the grid. And when they used to have the old meters, before the smart meters, we installed this for a customer, and you could see the meter actually spin backwards. That was pretty exciting for him.
Just a quick question. Do you know what the efficiency of the inverter is?
Yeah, it depends on the inverter. They're very high, like in the 95 kind of percent, quite high. But that's another key point for sure. You want to pick a good inverter for what you need.